This is problem number 9 on page 533, where we're supposed to find the sum of this infinite geometric series if we can, and if the series has no sum, we're supposed to say so. So we're looking to see, does this series, does the sum converge to a single value, a finite value, even though it's an infinite list of numbers. And you see, it appears that they're getting smaller, so we think it is going to converge. Anyway, so what we need to know to be able to find the sum is we need to know the first term, so that's 3 root 3, and we need to know the common ratio. So I'll just take a value and multiply by the value in front of it. And I'm just going to go ahead and simplify that to negative 1 over the square root of 3. And I'm not going to rationalize it yet because there's a lot of different orders you can do some of these steps in, and I'll save that till later. But anyway, if I take this, if I take this term and multiply it by the common ratio, I get negative 3. If I take negative 3 and multiply it by this, I get negative 3 over the square root of 3, and when I rationalize it, I do get this. And then when I multiply this by negative 1 over negative 3, I get negative 1. So it is the common ratio. That's going to work. So now I say, okay, so the sum of this as an infinite geometric series is the first term of 3 root 3 divided by 1 minus the common ratio of negative 1 over root 3. So let's write that as 3 root 3 over 1 plus 1 over square root of 3. Now, one really quick thing I can do without, fully rationalizing this is I could multiply every term here by root 3 in the numerator and the denominator. So I'm going to kind of multiply by a big one in the form of root 3 over 3. What that will do in my numerator, I'll have 3 times the square root of 3 times square root of 3, or 3 times 3, which is 9. Down here, I'll have 1 times the square root of 3, so I'm using distributive property, plus the square root of 3 over the square root of 3 is a 1. And then I can rationalize this to get this out of the denominator, being in a binomial, and I can multiply by its conjugate, root 3 minus 1, in both the numerator and denominator. So in the denominator, I'll have square root of 3 squared, which is 3, minus the 1 squared. And in the numerator, I'll have 9 root 3 minus 9. So I get 9 root 3 minus 9 all over 2. And that would be a simple expression of the sum that this value of numbers converges to. Okay, that's it. Oh, yes, I did want to make sure that this was less than 1, and the square root of 3 is definitely more than 1, so the denominator is bigger than the numerator, so the absolute value of that is less than 1, which was why we knew that it would converge.